Hello, welcome to this video. In this video, I'm going to be talking about how to implement closed loop control of an inverter. In this case, I'm going to be using the PIC24 as an example. So this video is basically going to be covering how to go about the firmware for closed loop control of an inverter. So over here, for starters, is to essentially show the basic schematic of a full bridge inverter. So over here we basically have two half bridges, and in this particular example we're going to be utilizing the unipolar control scheme. So before I get into the other aspects, I just want to give a brief overview of what sort of hardware what one should be expecting with regards to the hardware. I imagine if you're looking at this video, you're particularly interested in how to go about the firmware for this, the general idea behind that. So you might already be slightly familiar with an inverter. If you're not, essentially what an inverter does is it takes a DC signal on the input, and on the output it creates an alternating signal, an AC signal. So this is obviously very useful with grid tied applications, situations where you have a battery but you obviously need a particular voltage source similar to mains. For instance, from a 12 or 24 volts battery source, you could get 230 volt AC waveform, 230 VRMS specifically. And obviously in other places, I believe it's 120 volt RMS. But generally, that's the primary use case for inverters. So in this case, I've got a Proteus simulation running where I'm using a full bridge inverter. In this case, the input is 400 volts. And we said we have the full bridge, and on the output, we have an LC filter. In this case, I've added resistance to the inductor and the resistance to the capacitor, because in real life scenarios, they are not particularly perfect. These are not perfect components. And anyway, in reality, you do not want to deal with perfect components. You sort of want some, I guess, a parasitic resistance. Helps with dampen as well. And over here I basically have a 200 ohm load, and yeah, so I think I'm gonna link a video in the description where it talks about designing an LC filter. There are tons of ways to do that. There are actually more creative configurations for filtering for inverters. It's basically the topic in itself. It should be, taken very seriously. So I'll link some videos in the description. You could have a look at where they discuss things like that. This video is basically going to be focused on the firmware aspect of things. All right, and so those are the MOSFETs. Now jumping over to driving them. So over here in the simulation, I'm using the IR2184 half bridge driver. As you can see here, it essentially takes a single PWM input, and what it does, it produces an output, half bridge output. In this case, I'm running it in a quite, I suppose, a quirky way. So for the high side, I'm supplying it with a separate power supply, which is in this case 15 volts. So that goes between the VB and the VS pin. And essentially the high side MOSFETs are going to be driven with the HO pin relative to the VS pin. So it will have its supply of 15 volts between the VB and VS. Obviously the low side gets the supply from the VCC. So obviously, due to the fact that we have a full bridge, essentially two half bridges, we're going to require essentially two MOSFET drivers, two half bridge drivers. And so this is going to be the one for the second one. So I said PWM1 and PWM2. And obviously, just going back up here, and obviously we have gate resistors, MOSFET gate resistors, and also pull down resistors from the gate to the source. The primary responsibility of this resistor, the purpose, let's say, is basically to ensure that the gate of the MOSFET is discharged when you in fact do not want it on. So you want to turn it on and turn it off. So the pull down MOSFET is to ensure it goes off. By default, it stays low relative to the source. So if I click on that, I just use the value of 5K. You could use 10 kilo ohms there. And over here, I just made that resistance 56. It's important to note it's a balance over here. Obviously, if you go too low, then you might have ringing on the gate. And if you go too high, obviously it's not going to turn on quickly enough. So it's a delicate balance between the two. As you can imagine, the gate of a MOSFET, essentially what you're doing is charging up a capacitor on the gate. So it's all about, it takes essentially charging the capacitor every time you turn on the gate of a MOSFET. And next we have the microcontroller in this case, which is taking a single input, which is the output voltage, and the output of the system is essentially the PWM, PWM1 and PWM2, which we're gonna obviously touch on in more detail. And obviously with regards to the sensing the AC voltage waveform, there's several methods. There's obviously the transformer method, where you basically send this output directly into a transformer, and then the other side of the transformer you offset that voltage, and essentially you can read that directly from the microcontroller. But I prefer this method, utilizing sort of like a differential. You're essentially using a differential amplifier with an offset. So in this case, we're utilizing an offset of 2.5 to make sure 0 volts is in fact 2.5 volts. And obviously I'm saying 230 kilo ohms, so it's basically decreasing the output voltage by a factor of 230, which is evident by 230K and 1K. In reality, this should be much higher. You want to make sure you have your sensors high impedance and not low impedance. Is going to be a problem if these values are too low. Heat dissipation as well, depending on the size of resistors you want to use. You do not want to go too low with these values. So I simply chose 230 and 1K to sort of make it obvious that I'm decreasing the output voltage by a factor of 230. And just show that it's also, that's 230, 1K down there. And obviously that's the output. And if you want to be extra careful, you could buffer this again. Just keep in mind, if you buffer it again, it will affect obviously the speed of your system. If it will compromise the speed slightly, not extremely noticeably, I imagine, obviously depending on the kind of op amp you choose and the bandwidth, etc. But it's important to note you also have that option to obviously buffer this again. Generally speaking, any sensing going to a microcontroller should be buffered and protected, because you want to protect your microcontroller. You want to protect the pins. They're quite delicate and they have maximum voltage ratings, etc. So that's about let's say the schematic of what the firmware will be tested on. This is a basic schematic. This obviously in the real live scenario. I'm actually going to link an application note as well. There's several things that need to go into the system. Obviously, with real life hardware, there's several things as well one must take note of. Obviously, there are tons of more protection. As you can imagine, over here, there's probably going to be a EMI filter, and there's going to be an EMI filter going out as well, because this is an AC output. You want to make sure it's safe, and obviously tons of protection as well, because we are dealing with AC, which is quite unsafe if you're not careful, if it's not earthed properly, etc. So this is just a test setup. All right, now moving on to essentially the general, I just looking for the right word, maybe general theory of how an inverter operates. All right, so the purpose of this script is essentially to visualize what's going on over the reference period. So the reference period in this case is determined by the reference waveform, which is the sine wave. So over here in this particular script, I'm describing the triangular wave as the carrier wave, because the carrier waveform is in fact a triangular waveform. It could be a sawtooth waveform, because it determines the switching frequency of the MOSFETs, but or IGBTs, depending on what you use. But I'm just going to be using those interchangeably. So first off, I'm just defining the switching frequency of the carrier waveform, or perhaps the frequency of the carrier waveform. So in this case, it's 2 kilohertz, but actually it's supposed to be more higher than this. But the purpose of making it low in this case is so you can it can be visualized properly. You can see more easily what's going on. And the reference signal frequency in this case is 50 hertz. So it's 50 hertz in Europe, but 60 in some other places. And I think in America it's 60 hertz. And obviously this is a time vector, which in this case we're going to be plotting over 14 milliseconds. So first off, the reference, there are two reference waveforms for unipolar switching. So each half bridge gets a reference sinusoid. And basically the reference, so this is the reference of the first. It's simply a sine wave over the reference period of 50 hertz. And the second sinusoid is going to be basically 180 degrees out of phase from the first one. And next, this is defining the triangular waveform. This is the carrier waveform, and that's obviously determined by the switching frequency. And to generate the PWM signal, we're essentially going to be comparing the reference signal to the carrier signal. And essentially the PWM, the output of this comparator is going to be 1 when the reference is greater than the triangular signal, in this case greater or equal to the triangular wave. And obviously the same goes for SPWM2, only in this case we're going to be comparing the second sinusoid to the same carrier waveform. And that's essentially it. That's essentially how this works. The purpose obviously of this is just to basically visualize. So I'm just gonna go ahead and show the plot. All right, so I just zoomed in there. I'm gonna have to zoom back out. All right, so essentially in the red, we have the reference sinusoid for the first half bridge. And in the green, we have the reference sinusoid for the second half bridge. As you can see, they're 180 degrees out of phase from one another. And in the blue plot, we essentially have the carrier waveform, and this determines the switching frequency of the MOSFETs. And basically, we're going to be dealing with this from switching periods to switching period. So if we consider this, let me just zoom in. So if we consider this particular switching period, which is determined by this, so we're going to go up and then down. We're basically comparing the reference waveform to the carrier waveform. So essentially the output is going to be 1 in this region and this region. So if I could actually zoom into that part down here, we'd be able to see it more clearly. So that's 0.001. Oh no, that's further back. Okay, if you look at 0.001 to 0.9 over there. So as you can see there, so the red denotes SPWM 1. So as we can see, it's going to be 1. It's going to be 1 during that region. And it's going to be 1 during that region. And during the region where the carrier waveform is actually above the reference signal, as you can see here, that's going to be 0. The output's going to be 0. And the exact same goes for the second half bridge, which is sine 2 reference, which is the second sinusoid. Only this time we're going to be comparing the green to the blue as opposed to the red to the blue this time. And the same goes there, so it's going to be 1 during those periods and those periods. So as you can see, it's a wider area of 0 where the output's going to be 0. And obviously when we're talking about the first half bridge, this is going to directly determine the PWM of the first of the top MOSFET. And obviously the second, the bottom MOSFET is going to be complementary of the top MOSFET. And the same goes for the second half bridge, where this essentially determines the duty cycle for the top MOSFET in the second, and the bottom MOSFET is going to be a complementary of the top MOSFET. Look at that in more detail later on. All right, and that's about it. But obviously, as you can imagine, you might be wondering why this was shown. Well, this is just to sort of I suppose an introduction into the next part, which is basically deriving the duty cycle for this. So essentially you might be thinking, how do you determine the duty cycle? How do you calculate that duty cycle rather over this particular reference period? So how are you going to determine what the duty cycle should be during each switching period? Well, you actually suppose I shouldn't go into too much detail here, but in the next part, let me just say, it's just going to be based on essentially calculating, deriving the formula to calculate the duty cycle at essentially any instance of this particular sinusoid. All right, now to jump over to explaining how to derive the duty cycle for each point. All right, so before I actually do that, it's just important to explain what's going on here. So essentially, to achieve this, as you can imagine, we have to constantly change the duty cycle. But using a microcontroller and coding a firmware for it, you might not want to use a comparator. So essentially, you want to load a particular array with duty cycle values. And essentially, you want to run those duty cycle values with a specific time delay in between them. And through your inverter, and then after the inverter, obviously you get a filter, and then you get a particular sinusoid. And actually the shape of your sinusoid, essentially how smooth your sinusoid will be in the end, is determined by how often you're changing the duty cycle, as is shown down here. So essentially it all depends on how much space you have in your microcontroller. Obviously the idea is to have, I suppose, infinite changes in the duty cycle, but this is not realistic. So you sort of have to limit how large your array is. But before you do that, you essentially have to we have to come up with a formula to actually calculate what that duty cycle should be at each instant. So let's say you want to change it to 100 times, or you want to change the duty cycle to 100 times over the reference period. We need that formula to calculate essentially those 200 individual unique duty cycles for both arrays, for array 1 and obviously array 2. All right, so just jump over to the explanation. All right, so to get started. So essentially, what I've done here is I've essentially zoomed into the switching period. So the switching period obviously is the period of the carrier signal. So in this case, like I said, with that previously, that was 2002 kilohertz. So essentially the switching period would be 1 divided by that, by 2000. So in this case, we are making a simple assumption. We're basically making the assumption that for every switching period, during the switching period, the sinusoid essentially remains constant. The reference signal rather remains constant. And that's a decent, or that's an assumption that actually makes things a lot easier. So if you take the carrier signal, you can actually split it up into two parts, Y1 and Y2. So if we take a look at SN, so SN is basically the reference signal. If we take a look at where they actually intersect, where SN and Y1 intersects, that's actually a point of interest. And we take a look at where Y2 and SN intersects, that's another point of interest. And obviously, as you can imagine, to calculate the duty cycle, that's going to be determined by the on time divided by the total time. In this case, the total time obviously is the switching period, which is determined by this entire length. I should actually label that. But this entire length, the entire triangular wave, the base of it rather, is basically going to be the switching period. So the first thing we're obviously going to do is define this particular function y1, and that's calculated to be that, and y2 is calculated to be that. And obviously the variable t, because we're dealing with time here. And obviously the equation, well, the formula to determine duty cycle, this is just the inverse formula. That's t on divided by tsw. So the time spent, where Sn is above the carrier signal. So it's basically that time, and that time divided by the total period. So if we call this point the intersection of Sn and y1, if we call that t1, and we call the intersection of y2 and Sn t2, we can basically determine the on time to be t1 plus tsw minus t2. So essentially this time, tsw, well, the switching period, let's say, minus t2 is essentially this time over here, from there to there. We're going to take all of that and divide that by the switching period, and that gives us the duty cycle for that particular instant. Moving on. So now we actually have to calculate this T1, the actual T1 and the actual T2. It's better to just work in variables here, so you can just do everything and just, I suppose, plug and play in the end. And so to calculate variable T1, you just replace it with that particular T value there. And obviously the Y point is Sn, the X point is going to be T1. And making T1 the subject of the formula, this is what's calculated. And for T2, we do the same, only this time we're going to be dealing with Y2. And T2 is calculated to be that. And if we plug everything back into the formula for dt, duty cycle, we have T1, which is going to be that, plus the switching period minus this value, and all divided by the switching period. So in the end, the duty cycle is going to be equals to half multiplied by Sn plus 1, the sinusoid plus 1. And this particular SN value, obviously it's basically calculated by taking the sign at that particular instant. So this value should be between 0 and 1 always. As we can see from this formula, the duty cycle typically should be between 0 and 1. And if you take this, so that's basically going to be 0. So if this value is 1, the total value of dt is going to be 1. And if this value is 0, the actual final value is going to be 0.5. So essentially, your minimum duty is going to be 50%. Your maximum duty is going to be 100%. Typically, you don't want to go to 100%. You want to, hover about, I suppose, 95%. That's usually what I go for. But yeah, so that's essentially our duty cycle formula. So now we have to essentially take this further. Essentially, we're going to have to find the sign. That's basically the sign, taking the sign at that particular instant. So this equation there, the array size obviously determines the amount of times you want to change the duty cycle, and n is for that particular instant. So as you can imagine, n is going to be between 0 and the array size, not inclusive of the array size. So essentially, if your array size is 513, if there are 513 elements in your array, n is going to go from 0 to 512. And as you can imagine, the duty cycle for half bridge number 2 is going to be exactly the same thing, but 180 degrees out of phase. So we're going to add a pi to that. And now moving on, dealing with the amplitude modulation index. So this essentially determines how the magnitude of the sinusoid, and this is very important. And we determine the magnitude of the sinusoid by modifying this particular element. I used to make a mistake previously where I'd actually multiply everything by MA, which is the amplitude modulation index. So that sort of gives kind of, I suppose, interesting results. Let's just put it that way. But typically you want to only multiply this term by MA, which is the amplitude modulation index. So, say 0.5 MA multiplied by sine. And that's that. And now we can actually use this to generate the duty cycle array in the firmware. So this is essentially the process to derive the formula. So I'm going to include this document so you just take a closer look at it and just, I suppose, familiarize yourself with it. So just that's basically, I imagine there are other methods to essentially calculate the duty cycle, but this is one that is, I suppose, easier for me to understand. And let's say MA, actually I should define that as well underneath. So MA typically should be between 0 and 1 as well. You typically should try not to go above 0.9 or 0.95. It's not advisable, and an MA greater than 1 is just a very funny looking sinusoid. It's like, you're essentially maxing out before the maximum point of your sinusoid, which you're gonna get a funny shaped waveform at the end for sure. All right, that's essentially it. And now I'm just gonna be jumping over to the firmware. All right, so now to take a look at the firmware. So essentially, this is the aspect where we're going to be coding the SPWM routine and describing the closed loop control of the system. So essentially, to get started, I'm going to do a brief overview of the structure of the firmware, of the control code. So to get started, so in the main.c file, basically the arrays are initialized. So in this case, I'm utilizing a 100 element array. So the resolution is not that high. There's a reason I chose such a low value. Typically you want this value to be, I suppose 400, where you have 200 every 10 milliseconds. And obviously 400 for the 20 milliseconds in the case of a 50 hertz wave. 50 hertz sinusoid frequency. All right, next you essentially want to define the array. So assign one array for the first half bridge, assign two array for the second half bridge. It's a float array initialized with 0.0 on each point. And the next, we're initializing the modulation index to be 0.65. And over here, VAC, that's going to be the sensed value of the output voltage. And VAC ref is obviously the reference, initial reference voltage. So these variables I'm actually going to explain in more details once we take a look at the function. And VAC HDH is to do with essentially the closed loop control of the system. So they're actually, I'm going to present sort of two methods to go about closed loop control of the system, specifically output voltage control of the inverter. And I is just basically an index, so it's just initializing that value to 0. And this actually is also to do with the closed loop control. And now ref sign table. So this is also to do with, well, pretty much most of the variables are to do with closed loop control. So they're not going to make a lot of sense until I sort of explain the functions individually. So over here, the first thing you want to do in such a case is obviously to define, to calculate the variables for the sinusoid is essentially load the duty cycle values. So this is essentially, these are essentially those duty cycle values, or rather, let's say a part of those values to help us calculate the duty cycle. Let me explain it more. Is exactly what I mean. So if we take a look at this Word document, this is essentially the aspect we're calculating at this point in time. So that's essentially going to be an array, 100 element array. And this is essentially what we're calculating first. And then later on, essentially what we're going to be doing is we're going to be multiplying that value by the amplitude modulation index, and essentially calculating this true duty cycle value. So I'm just going to go back. All right. So that's basically the first part of the system. But before I carry on, this is sort of like a, I suppose, soft initialization. I think it's actually better to talk about the initialization of the various peripherals and what we're dealing with. So if I go back here, go over here. So I'm basically in the Mplab code configurator tool. Basically makes coding the system much easier. It takes away a lot of hassle, I suppose. A lot of work is done in the initialization. Essentially all you have to code after that are the functions. So it sort of helps a lot with that. So first off, we go to the system module and essentially going with the maximum frequency of the oscillator. In this case, that's 32 megahertz. And obviously PLL is enabled for that, so everything is set up as follows. And with regards to the pin module, interrupt module, I'm not really doing anything with that. So essentially the peripherals we're utilizing in this case are the ADC peripheral and the PWM peripherals. So if we take a look at the PWM peripheral, so we go over to timer 2. It's important to note that in this case, the switching frequency is selected to be 15 kilohertz. Typically with the inverter, you could go up to 20 kilohertz. Well, you could actually do as high as you want, but typically you keep it around 15. In this case, it's 15 kilohertz, and an advantage of this as well is great PWM resolution as well. In terms of the variations of duty cycle you could do. Obviously, in this case, we're only utilizing 100 unique duty cycle values, but obviously with a lower switching frequency, you have a better resolution. So essentially, to set up PWM1 and PWM2, so what I mean by that is PWM for each PWM signal for each half bridge. So essentially, want to set up the timer first to operate at 15 kilohertz switching frequency, which is symbolized by 66.67 microseconds. All right, so the next step is to go to the output capture module. So we're going to go to OC1. So OC1 typically, OC1 will be used for PWM1 and OC2 for PWM2. So the output capture module, you select the mode to be PWM mode, and OC fault pin is disabled. And you want to make sure your source is timer 2. And there you go, that's about it. And the same thing on OC2, you go to PWM mode and OC fault pin is disabled. And that's it. The next thing you want to do is you actually want to go to the side here, and you want to right click on whatever buttons you want. So you could just what you want to assign. Obviously, we could assign this to be OC1 as well, but obviously I have already selected that to be pin number 21, RB10 for OC1. Pin number 22 is OC2, which is an output. And the next aspect obviously is for feedback. We need to sense the voltage of the system. So for feedback, we essentially use AN0 in this case, which is AN0 of the ADC. So we're just going to go over to the ADC setup. So the first thing you want to do is you want to select the conversion clock source, select the RC clock. You want to go over to the conversion trigger, select that to be the internal counter, end sampling, and starts conversion. Obviously, clearing the sample bit, end sampling, and starts conversion. This is more of like a manual sort of ADC. It doesn't automatically convert. You sort of have to clear the sample bit to start conversion, to end sampling, and essentially start ADC conversion. And obviously you could use int0 as a trigger as well, or timer 3 as a trigger. In a sense, you will have to set up timer 3 to send a trigger on the output. So it'd be sort of a time system. It's also quite advantageous if you want to set up sort of like a timer interrupt or a control loop, where right after conversion it goes into that loop and it executes that. So, but in this case, we're just going to be utilizing the internal counter, so it's going to happen automatically. And our acquisition time, because I'm looking, my focus is accuracy, so I sort of went for the maximum, which is 31. Also, you got to be careful in this case where you don't want to go too, low. Obviously, you get a fast acquisition time in that case, but you also want to make sure your acquisition time is as long enough to get accurate results. All right, so just selected that to be 31. So the positive voltage reference, AVDD, and the negative voltage reference, AVSS, obviously that's basically going to be whatever you're powering the microcontroller with, 3.3 volts or 5 volts. I actually believe this microcontroller only takes 3.3 volts. And the negative VREF, that's going to be ground. All right, and next, basically, you're going to right click on wherever pin you desire. And you're going to select that to be the input. I've selected pin number 2 to be the ADC input, and it will appear over here. And what you want to do is you want to enable scan. And you want to enable, obviously the ADC is enabled once you choose it, but you also want to enable auto sampling. It's important that you do that. And essentially that's how you set up the ADC. And once you're done with that, then we go on to the final aspect, which is to do with closed loop control. We're going to be utilizing a timer interrupt for closed loop control of the system. So I'm essentially using timer 1 for that. So essentially every 200 microseconds there's going to be an interruption. Like I said previously, depending on how many times you want to change the duty cycle is going to determine your timer interrupt time. So let me just go back to explain it better. So let me just add another section there. So that's going to be timer interrupt time is basically going to be all right. So that's basically going to be the the reference period. So that's going to be Tref. Yeah, I think I'll just call that I'd find a better name. So the reference period. So for 50 hertz, that's basically going to be 20 milliseconds. And the bottom part is basically going to be the number of times you want to change the duty cycle across the reference period of 20 milliseconds. So in this case, we want to change it to 100 times. Oh, well, let's say array size actually. And call that array size. And in this case, the Tref, just go back, make a fraction, is 20 times 10. Oh, well, it's actually to the power of particular value times 10 to the power of -3 seconds. And the array size is going to be 100. And basically, we're going to equate that to, that's basically going to be 200. I'm not opening that. Let's go to symbol, microseconds. All right, so that gives us 200 microseconds. So obviously, if your array size is more, you just substitute as you would like, and obviously your Tref, which is 1 divided by your reference frequency. Obviously you would adjust everything as they should be, and you would get that particular value. So I'm just gonna go back to the firmware, and that's why that's been set up to be 200 microseconds. And that's about it for the initialization of the firmware for this. Just to recap, first you want to set up the switching frequency for the MOSFETs, which is 15 kilohertz, and then the period is going to be 66.67. And then set up timer 2 for this. You can also use timer 3. This particular microcontroller has a limited amount of timers. It's just something, yeah. Well, it does have 5 timers actually, but I believe for the PWM it's just timer 2 and 3. All right, so once you set up that timer, then you want to go over to the PWM, which is the output capture module I'm using in this case. You want to set them up in PWM mode. For OC1 and OC2, make sure you select the source to be timer 2. And next, what you want to do is you want to go over to the ADC, set that up. First, conversion clock source, acquisition time to be 31, conversion trigger to use the internal counter so it does it automatically. You want to set up the reference. These two are actually done by default. Essentially what you have to change are the conversion clock, conversion trigger, acquisition time, and obviously you want to set up the pin that you're going to be utilizing. And also you want to enable, obviously ADC is enabled by default, and you just want to set up auto sampling. Set that up and obviously scan enable. And that's that for the ADC. And lastly, you want to go over to the timer 1 And obviously this value is dependent on how many times you want to change your duty cycle across the reference period. And essentially you're going to be using that formula as defined in the end. You want to use this formula to determine your interrupt time. In this case, the reference period is 20 milliseconds for 50 Hertz, and the array size we've chosen is 100. Obviously, your array size is going to be highly dependent on how quickly you can implement a control loop, like in terms of how fast is your control code. I've chosen a conservative time of 200 microseconds because this microcontroller I'm utilizing is a little bit slow. Obviously, for more advanced digital signal processors, it's a bit quicker. So that's about it. So let's just go back. All right, so once you're done with that, you just generate. I just like to do it twice just to make sure. And now we can basically dive into the aspects of the code that we'd like to change. Now over to the first parts. So as started previously, since all the various peripherals have been initialized, the first thing we want to do is essentially want to fill up this array. So we utilizing the for loop for this. Obviously, this loop starts from uses the variable I as basically an index, and it's essentially gonna automatically assign sign values for each element from the 0 element to the 100th element, because it's a 101 element array as is defined here. So obviously it's just as stated in the formula. So basically going to be sine f I divided by array size multiplied by 2 multiplied by pi. In this case, m pi is obviously that's the value of pi, and essentially that's going to be multiplied by 0.5. So as described previously, it's basically computing the first aspect of the duty cycle formula, and then we're going to utilize this later on. So I'm just gonna, the same thing is done for sine 2, for the sine 2 array. So essentially, just to re-explain, we are doing this aspect first. We're calculating that, and we're calculating that. And obviously, we can't just type this out in a firmware just that way. We basically have to put it into a for loop and compute this value from for 100 values that we want to store in an array. All right. So, and we do the same for the reference sign table. So this will come into play later on. So this is actually for the reference. This is specifically for closed loop control. All right. So in timer 1 is essentially where everything happens. So if we go over to the function, the T1 interrupt function, I'm just going to comment that out. So the first thing we want to look at is the system in open loop. So over here we basically have one PH control OL. So I'm going to jump over there. And essentially what we have here is basically external float. So we have access to the array that we defined in the main function, in the main.c file. We do that to also have access to the sine2 array, and obviously the amplitude modulation index, and obviously the element I. And we're just defining 2 local variables, PWM1 and PWM2. And essentially, PWM1 is calculated as follows. So this is the full part of the duty cycle equation, as you can see. So this aspect already has 0.5 in it. I think I should zoom in. Make this more. All right, that's more clear. So this aspect was already calculated. This particular element, we're essentially reading that from the array. the array that we've already pre-populated at the start, well, calculated and populated that array. And now essentially what we're doing is we're multiplying by the amplitude modulation index, and we're adding that to 0.5, and we're completing the system. And obviously that gives us a value between 0 and 1. In the microcontroller, that's not very useful, obviously, 0 and 1. Well, it is useful, but it doesn't really make any sense from a PWM peripheral perspective. We sort of have to scale that over to a system that the peripheral can actually utilize, and that's why we'll multiply by this value. So the max duty, I'm just going to jump over to that for a bit. So it actually gives us the maximum value of the period register, of timer 2 period register. As explained earlier, we're essentially using the timer 2 as to generate the PWM. The output capture module is generating the PWM, but it's using timer 2 as a base to do that. So essentially the PWM is generated using a counter system. So it counts up and then goes back to 0, counts up, goes back to 0. So that's actually done in timer 2. And then the output capture module does the comparison of that. And then out of that, we're able to modify the duty cycle. So if we go to timer 2 period 16-bit get, so you can actually go there and it returns the value of PR2. And PR2, if we go back to over here, so this is actually the value in the PR2 register. So what we did over there is basically we just took a quick shortcut. Instead of constantly writing this every time we use a max duty definition, we just simply call this function and it gives us the PR2 register value. And obviously we've assigned that to the max duty. It's not a variable, it's defined, so it's always going to be that value throughout this code anyway. And essentially that's what we have there. So just to give you some reference, essentially what we just did here, what's been done is essentially this, the duty cycle 1, and obviously for duty cycle 2 it's basically that. Obviously this array has been populated already, and we're just multiplying by the 0.5 has been done with that to take away a lot of work, and we'll just multiply by the MA, add that, and obviously the D1, okay, I actually should have put this down as well, and where, and so I'm just gonna say D12, D1T, and D2T are both between 0 and 1. So they're both between 0 and 1. We basically have to scale that up to what the microcontroller can accurately deal with. So we just multiply that by the max duty, and it scales that appropriately, and we just send our OC1RS is basically how we modify the duty cycle for the OC1 for the output capture 1 module, and OC2RS is how we do it for output capture 2 module. So obviously the maximum value of OC1RS is the value of the PR1 register. OC2RS will be the PR2 register. And obviously we sort of have to keep track of the element we're gaining access to in the array. So essentially after we access this particular I suppose element of the array, we're basically making we're incrementing the array, so we can have access to the next element. So it's going to be I++, and basically ensure that we're not trying to access a value that's non-existent. So once I value is greater than array size, once it's greater than 100, like we defined earlier, it's going to go back to 0. So this is basically, in essence, resets the array, so we can basically do the cycle. We can redo the cycle over and over again. So this is actually the PWM routine, and obviously from the output of the microcontroller, that goes to a half bridge driver, and then it drives the full bridge inverter. So let me just go ahead and run this and show the functionality. All right, just to make sure I got it right. So I've set up the MA to be 0.65. I guess I could just reduce that up to just check. All right, I can change over now to a different view. Okay, so let's just zoom in. All right, so tagged 2.L1 and L2. So I can just go there, edit graph. Well, so let's change that time to 300. Actually, just make it so it goes quicker. 250. So we'll just add traces, probe L1, L2, and we're just gonna say L1 minus L2. So we're just gonna name that L1. All right. So just gonna go, well, close that and base. No. Well, it seems like it's actually gonna take a while. Let me just go ahead and fast forward this section. Well, I'll just skip over to once it's done, so we don't waste time. All right, so basically we're almost there. So essentially the amplitude modulation is about 65%, so it's about done. I'm just gonna jump over to that, and there we are. As you can see, there's a bit of a wiggle over there and there. Basically that can be attributed to the fact that the resolution is not that high. So essentially we're doing 50 changes for every 10 milliseconds, and well, 100 duty cycle changes for every 20 milliseconds, which is not excellent. So we look at that, so it's basically 262 volts peak to peak. All right, and obviously this time region there is basically the time it takes the microcontroller to calculate. So it takes about 70 milliseconds to calculate all the values for the array and just to populate them. So now I'm just going to go back to the firmware and change and basically change the amplitude modulation index. I'm going to take it low to the low first, and well, I think I could just take it higher actually. Just take it higher. So MA was that. I'm just gonna take that to 0.8. Oh no, that's 0.9. That seems to be a good number. 0.9. All right, so just gonna go back, open up Proteus, and run it again. Oh, I'm just gonna sort of skip to the end to save some time. All right. It's basically almost there. Okay, so it's just gonna say okay. And there we are. Well, it's a bit higher than normal than what I desired. But it's about 358. Well, typically you essentially want something like 325.269, which is 230 volts RMS. I guess in some cases you'd want 220 volts RMS, essentially a lower amplitude modulation index. All right, so that's about it for the open loop aspect. Obviously, the time it takes to calculate is still sort of constant. So now I was basically gonna jump into discussion of the closed loop, or the first method anyway. All right. Now to explain the closed loop control of the inverters. So as stated earlier or discussed lightly earlier on, there are basically two methods that I know of to basically accomplish closed loop control of the inverter. Well, two methods with regards to voltage mode control. So I'm just gonna go ahead and then explain I suppose the simpler method. So in this method, just to explain it simply, in this method, you're basically gonna be tracking the highest point of the inverter. We're basically gonna be trying to sense the peak of the inverter and just basically trying to follow that. So let's just go over to, well, it's better if I explain with paint by just doing a little sketch. All right, so essentially, just make this, yeah, that's thick enough. So let's say we have a, oh no, I think, no, want is a pencil, decent thickness, yes. All right, so essentially what we have is a sinusoid. Oh, this is a badly drawn sinusoid, but yeah, it'll do. So essentially this is a sinusoid. And essentially with the first method of closed loop control, which I think is easier method, essentially we're going to be trying to track this peak from cycle to cycle. This peak, that's all we're going to be sensing in the code. Well, there's actually a way to do it in hardware. Obviously, you could use a rectifier and a capacitor, and automatically that gives you the peak. But it's important to note that if you're using this particular sensing method, it's quite slow. So essentially, we're just going to be sensing the peak, and then what we do afterwards, we adjust the amplitude modulation index. And so essentially what you'd expect to get would be something like this. So sense the peak, and then it goes down to the particular value that we want. Although if the set point is a little higher, it goes up like that. But essentially all the time we're sensing that. We're always sensing the peak. So we're going to be doing that every 10 milliseconds. And the reason we're doing it for every 10 milliseconds, actually in the code, I should actually do this in another color. In the code, what we're doing is we actually, once we sense this value, we sort of rectify it in the code. Right, so we'll change it to that. So everything is like that. So basically what that means is we're able to, instead of doing this every 20 milliseconds, like basically waiting, let's go back to black. Like basically, instead of waiting for us to get to this point every time before we start trying to sense the peak, we can basically just do the reset every 10 milliseconds. And essentially what that does is it helps us reach the set point much quicker. Although with this method, it should be noted that reaching the set point is, I suppose, disturbance rejection is a bit, response is a bit sluggish. Let's just put it that way with this particular method. All right, so let's just go back to the firmware. All right, so that having explained the methods, I'm just going to go back to timer 1 or to the timer interrupt. So basically, you still have the open loop running. So I'm just going to go to this particular method. So it's called the peak. Basically, I'm sensing the peak. I will just look at the definitions. Obviously, we have to call, I suppose, give access, give this particular function access to the arrays we've defined in the main function. Obviously, the amplitude modulation index, the I, to access each element of the array. SSTR, which I'll explain shortly the reason for this. And obviously VAC, that's actually the sensed AC current. AC voltage. And VAC ref, obviously, that's the reference. And VAC HDH, so this is actually a variable to monitor the peak. So I suppose I should rename this peak because it's just made more sense. The HDH representing the highest point of the VAC value, and VAC ref, AC mag, I believe. Not actually sure if this one is particularly necessary. Yeah, I'm not too sure this is necessary in this code. I might have just copied it from the other function. But as I go on explaining, I doubt it's necessary. But let's just carry on. So, and obviously the PWM variables are initialized PWM1, obviously for half bridge 1, PWM2 for half bridge number 2. And now, first off, you want to calculate the AC voltage, VAC. And the way we do that is this, the following formula. So, I kind of explained I briefly explained the kind of sensor used in this case. So let me just go back to it for a brief moment. And just explain it again. So it's kind of stays fresh and goes in with what. Alright. Just zoom into it. So essentially this is the sensor being used. So it's got a 2.5 volts offset. That's to ensure, because obviously the AC voltage goes through the 0 point and it goes negative as well. And the microcontroller cannot handle negative numbers. Well, it's at least this one is not configured at this point in time to deal with that. So essentially, we're going to offset everything by 2.5 to ensure the minimum value we send is in fact 0. And then the 0 point, the 0 crossing will be essentially 2.5. So it is basically have a 2.5 volts offset, and the signal is decreased by a factor of 230. So that's represented by 230k and 1k. Obviously, in reality, you want much higher impedance for your sensors. So this lower value would be somewhat a lot higher, and this might be in the mega ohm range. But I kind of just chose this ratio because it's kind of, I suppose, convenient and relatively straightforward to kind of understand. This is 230, this is 1k, 230, 1k. So essentially, our sensors, our output voltage has been decreased by a factor of 230, and that output obviously goes to the N0 pin of the microcontroller. All right, and just go back to the memory. So now essentially that's what the actual hardware sensor is doing in this case. And so in essence, to take that, in essence, the microcontroller gets this value from a scale of 0 to 5. And to convert this back into an actual voltage, the first thing we do is we actually compute this equation here. So actually, I think I should probably put another comment, well, right before, to sort of explain what each part is. So obviously the ADC buff 1, that's, I'm going to call that ADC, the raw ADC, ADC val. Right, so that's going to be the raw ADC value. So in essence, after you get the raw ADC value, you need to convert that to an actual voltage. So the way we'll do that is basically we take the VREF and then we divide it by 2 to the Alright, 2 to the power of, let's just represent to the power of ADC resolution. So in this case, the resolution of the ADC is 10 bits. So 2 to the power of 10 is 1024. Try to be as accurate as possible. So technically it's 1023 because it's 10 bits. Actually 1024 would be 11 bits and 1023 would be actually 10 bits, but it actually doesn't matter that much. So you could just use 1024. And essentially once you do that, you need to take that back down to, you need to deal with the offset. So you just say minus V offset. And once you do that, you get the actual voltage. You get the actual voltage of the output, but obviously scaled down. So you need to scale it back up, and then you just multiply it by your sensor gain. So in this case, the sensor gain is less than 1. Well, it's been decreased by that particular value, but in this case, we're basically going to have to increase by multiply by that particular value. In this case, it's been decreased by a factor up to 130. So we're going to multiply by that. I think I should rather just call it sensor gain factor. And based on what we chose, let me just specify. So the VREF obviously that's 5.0. The ADC resolution, that's 10. I'm gonna just do it like this. ADC resolution. Obviously, I'm gonna comment everything appropriately. So the raw ADC val. That's actually what you get from the microcontroller. Range from 0 to 1023. And obviously your V offset, so that value in this case 2.5, but obviously in your case you might choose that to be another value. Obviously you could use simple resistive divider to achieve 2.5 from 5 volts, and in this case the sensor gain factor is going to be 230. Okay, and you just do that, and that's about it. And that's it. And once we substitute into this equation, that's what we get. And obviously you want things to be as quick as possible. So obviously once the ADC conversion is complete, it's the ADC value, or the conversion value, is actually placed on the buffer register, in this case ADC1 buffer 0. So we're just taking that, we're typecasting that to a float in this case. And once this this equation is simplified, this is what we get. So this and this are essentially the same thing, but essentially it's important to note how you essentially get the actual AC voltage. All right, so once the AC voltage is obtained, like we stated previously, it's almost like we're rectifying the AC voltage in the firmware. So what you want to do is you just check if VAC is less than 0. You want to make sure that you make it positive. You can obviously take the absolute value of this particular code, of this particular equation, but the FABS does take it takes more time to do the FABS, if I remember correctly. Obviously you can check yourself as well, but it obviously last I checked, well, as far as I remember, it takes longer to do the FABS than it does to simply do an if statement. All right, and then the next line is essentially where we keep track of the highest value, and then we take the VAC value. Obviously, this is initialized to be 0, the highest, the peak AC voltage. So essentially check if the AC voltage is currently higher than the highest value, and if it is, the new highest value is obviously going to be that AC value. So essentially what we're doing here is we're just keeping track of the highest value. And now over here we have VAC ref. Let me just go back to the main. All right, makes sense. So VAC ref AC mag is seems kind of redundant, but so this is actually where we define the actual reference voltage, let's say. And as you can imagine, in normal operation of the system, sometimes the peak does change depending on your load. So sometimes the peak could be very high, sometimes it could go lower. So what you want to do is you actually want to reset the highest value after every 10 milliseconds. In this case, keep in mind that we're changing the duty cycle 100 times, so half of that is basically 50. 100 times represents 20 milliseconds, 50 times represents 10 milliseconds. So essentially we have this variable to keep track of that time, which is 10 milliseconds. So we're basically checking every 10 milliseconds for the peak value. So obviously if the SSTR variable, which is this, which we're incrementing every time we run this we run into this particular timer interrupt, so which is every 200 microseconds. So after 50, that will be 10 milliseconds. So once we go into it, basically know now that our actual VAC, what we want to be dealing with is the highest value. And then afterwards, basically have a what I call plus plus minus minus type of control system here, where we basically compare the VAC to the VAC ref, which is over there. We've equated to the actual VREF AC magnitude, and if it's basically less than the reference AC voltage, simple, we'll basically increase the amplitude modulation index by 0.005, by essentially 0.5%. And if the VAC, basically if the highest point is obviously greater than VAC ref, obviously we need to reduce the amplitude modulation. We need to basically reduce the amplitude modulation index value. And obviously you want to make sure that the MA value does not go above 95, well 0.95. And I want to clamp it to that and also make sure it doesn't go below 0.0. And afterwards, obviously, we want to reset the VAC and the VAC HGH. Obviously, it doesn't matter much if we reset the VAC value because we're recalculating every time. I understand it's a little bit weird, confusing kind of way. And obviously, the SSTR variable, which is that because we want to start and do it, only get into this loop. Well, this conditional once 10 milliseconds has passed. So that's basically that, and once we're done with that, basically calculate PWM1, and this time we're using the MA variable as opposed to a constant as it was with the open loop system. And the same thing with PWM2. And in the end, we equate that to OC1RS and OC2RS to those values. All right, and obviously we need to implement this every time because that just keeps track of the array. The I variable just keeps track of the element we should be executing at this point in time. That's just the way it's got to be with SPWM. So we'll always have the right duty cycle, utilizing the right duty cycle. So those are a bit, I suppose maybe there's a lot to take, but I will just do a quick recap. So first off, we're going to calculate the actual AC voltage. And next thing you actually want to do is want to rectify that. Actually, I think I should just comment that. Right, calculate AC voltage. And next thing, rectify AC voltage. And right afterwards, check if it is higher than VAC peak. Okay, so this is a bit confusing. VAC peak, actually, HGH, and then let me just do that and say that's VAC peak. Okay, so basically that's what we're doing, and this is actually redundant. This is actually taking up space. We shouldn't do this every. This should not be done every time. It's actually wasting time. Computational. I think I'll just the VAC. I think. Well, actually, let me just go back and leave it there. Well, assign in. Let me just say assign in the BAC ref. All right, and so here we're incrementing SSTR to keep track of time, and the time we're trying to keep track of is basically 10 milliseconds, or the positive half cycle, or half, or let's say 0.5 times the reference period, let's say. And in this case, it's 50. So, this should actually be divided by, this should actually be something linked to your array size. So this is going to say, should be linked to your array size. I'm just going to go ahead and make I'm just going to name it off tref, right? And that should be the array size divided by 2. All right. So then half tref. I'm just gonna go back to that part. So now this is supposed to be half tref, which makes more sense. It's better to have them as this sort of value, just in case you decide to change the number of elements you would like in the array. All right, so once you're done with that, basically, then right. So if incrementing, so this should be if has passed. Then we jump into it, and then we equate VAC to VAC HGH or VAC peak, which is also VAC peak. And over here, we'll basically increase or decrease MA based on VAC and VAC ref. Okay. And over here, all we're doing is we're limiting the MA. There's a limit in the MA. So after limiting the MA, we initialize VAC, HGH, VAC, peak. And actually making VAC 0 and AC, making VAC 0 is kind of redundant, so I just gonna take that out. Just took that out. And SSTR. Firstly, SSTR is basically we're able to keep track of the time, and we want to keep doing that, so we gotta make that 0. And that's about it. So I'm just gonna go ahead and compile. Well, almost forgot. Update PWM1 and MM2 variables and update the duty cycle for both half bridges. All right. And then lastly, you want to make sure that you keep track of the array element for the SPWM. Right, and obviously here restart the array if overflow occurs. And of course, overflow will occur once we get to the end of the array size, which in this case is 100. So we can start the sinusoid again. All right, so that's about it. So let me just run that. Okay. Actually, before this code can be ran, actually, it's important to note that due to the fact that this method actually takes quite a while to well, let's say get to the set point, you sort of want to make sure, well, in this case, not in reality, you can actually start the MA value as low as you'd like in the real world, but in here, for the sake of simulation and simulating quicker, I'm actually gonna start the MA value at something a little bit, I suppose, lower, so it could get there relatively quickly, so you can actually see it, so it won't take too long to simulate. So just gonna run that, and the set point in this case, which is VREF AC Mac, this is actually, I suppose, let me just put a comment. This value must be your desired VRMS multiplied by SQRT2. So it doesn't, you can't just write your RMS value here. So over here, you notice this is actually 120 multiplied by root 2. So that's why we have this particular value. So I'm just gonna go ahead, run that. Okay. And I'm gonna change the view to Proteus. and just press the space button. Okay. So now we can see the completion percentage. So it's actually 19, so it'll actually take a while. So I'm just gonna skip right over to the end. All right, so kind of just it's right amount, almost done the simulation at this point in time. So should be done any time now. Okay, it's done. So we just open it. All right, there we are. So as you can see, so if I zoom in there, it's right around the peak, it's right around 170. As you can see there, it takes a couple of cycles to actually settle down because it keeps checking. It only checks every cycle, so every 10 milliseconds it'll actually check. And that's when you actually perceive a reduction. So it will reduce there, reduce there, reduce there slightly, until you sort of find a nice, decent, balanced point. And obviously, let me just go back to the firmware for a bit. Yeah, and obviously, we just head back to the function. And obviously, if you increase or decrease this time, if you decrease this time, it'll be more stable, but it will take longer to get there, obviously. And obviously, if you reduce this time, it'll get there quicker, but it'll be more unstable. So it's kind of have to find a sweet spot in between. And you can obviously use a more sophisticated equation, sort of like a PI controller, for instance, in this case. But in this case, the microcontroller, this particular one, is quite limited in terms of like the amount of well, processing time, let's say. So it will take quite a while to execute that. So that's why this is actually done. Okay, so so I think let's just go ahead and change the set point to 230, and now be 325. Oh, 325.269. And in that case, you also want to, well, for the sake of this example, I'm just going to modify the initial MA to be something a bit closer to, I suppose, the destination. So I'm just going to go with 0.9. Let's just go with something maybe a little bit lower, say 0.84 for the MA value. I'm just going to go ahead and run that just to get. And I'm just going to change back to Proteus over there and run that. Okay. I realize I actually ran it previously. Well, it's the same thing as we just saw. So let me just rerun because we just reloaded the code. All right. So know what the percentage is. It's about 17, 18. So I'm just gonna go ahead and skip to the end and not sort of waste any more time. Just sort of looking at a progress bar. All right. Seems like it's close to the end. Just gonna, yeah. It's 98, 99. Okay. All right, there we are. Seems like it's actually pretty close already to this particular value. So there we are. So 323, 327. I suppose I should take it to something a bit lower to show a better demonstration of sampling in action. Well, it should be noted that in the actual implementation, you shouldn't bother with this. It's just for the sake of simulating and doing it in a timely sort of manner. Okay, going back to Proteus. I'm just gonna run that again. Okay. So I'm just gonna go ahead and skip to the end. Right. Kind of closer to the end now. Okay. All right, there we are. Well, not as dramatic as I hoped. As you can see, it kind of starts with lower, and it sort of gets to the set point, to the desired set point. So, yep. Well, that's about it. And as you can see, the sinusoid is kind of squiggly. Well, that sort of is owing to the sort of the poor resolution, only changing 50 times every 10 milliseconds or 100 times over 20 milliseconds cycle. So that could be obviously be greatly improved upon. And yeah, that's about it with this particular method, with the first method, which I would say is a bit on the easier side. But obviously, it should be noted that although it's on the easier side, there are some drawbacks. If you have a spiky signal, if your signal is your output voltage is spiky, or you have a wacky sensor, you're gonna have a really bad time. Or even without your sensor being wacky, if it's just a normal sensor, and your output voltage signal is kind of strange looking. Well, let's say it's got spikes, it might pick up one of those spikes as the maximum, and you just basically max out at 0.95 amplitude MA value. Or worse, it will oscillate from that to low, oscillate high, low, etc., which is very quite undesirable, as you can imagine. So that's essentially the first method in this case, which is the easier way to achieve the closed loop control of the inverter, which is, it's got positives and negatives. Now I'm just gonna jump over to the, I guess I would say the more reliable method. It's a little bit complicated. It's not certainly not complicated, not that complicated, I would say, but certainly different from the first method. But I'm just gonna explain it, and you'll find it very, very intuitive, actually. All right. Well, with the second method, what we're trying to do is we're gonna be comparing at every single point. So as opposed to just detecting the peak, we're gonna be comparing. We're gonna be using a reference sinusoid, the entire 100 element sinusoid. I think it'll be better if I use the Microsoft Paint at this point to illustrate my point. Right. So let me just go over there. Gonna need an eraser. Let's okay. I think I'm gonna have to. let me just create a new one. Sorry. All right. So essentially, because erasing basically take a bunch of time. All right, so we're dealing with the sinusoid here. So previously what we're doing, we're detecting the peak. So at this point in time, what we're going to do is basically going to have a sinusoid, right? Well, something that looks like a sinusoid anyway, but it's basically going to be a sinusoid. And essentially what we're going to be doing with the closed loop control is at every single point, we're going to be comparing with each point. So the reference voltage will keep changing for every point, right? And obviously, as stated previously, we're going to be rectifying it. So this is essentially what we're going to be looking at in the code. But we're basically going to be comparing at every single point. So just like that over the 20 millisecond cycle. So as opposed to just using the peak, we're going to be doing this at every point. And the major advantage, as you can imagine, is we're going to get to the set point much quicker, just by the mere fact that we're just going to be comparing at every single point. So previously, we're going to be waiting for every 10 milliseconds. So we're going to check at that point, and then at that point, which is, you know, it's simpler, but it does take time. It does take time to get to the set point. So, all right, so this is the general idea of what we're going to be doing. So let me just get back to firmware, go to timer 1, and I'm just going to comment this out and go over to the function and just essentially explain step by step what's been done. And at first, obviously, we have to define the fact that we're getting the array from the main function, obviously given access to this particular function. This array, so we're essentially able to use this array in the particular function, sin1 array, sin2 array, and now we're actually introducing the ref sign table. So I believe I had it in the other function. I had to take it out. So this ref sign table is essentially that reference wave that I just showed, and obviously with regards to this float, which is the reference, which will be changing at every single point. So the I value, the I variable, is going to be changing from 0 to 100, well, to represent each element of the array. So at each single point, the reference is going to be changing. So, and obviously we have VAC and VAC ref, and obviously the PWM variables. So obviously the first step, same as it was before in the previous function, we're going to calculate the AC voltage, and next we're going to rectify it. And obviously now we have to equate the VAC ref. So now this is where it gets a little bit different from the previous one. So as you saw previously, we just equated it to a single reference, and that reference stays constant for, well, the reference does stay constant for the entirety of the sinusoid. Obviously we're checking every 10 milliseconds, but it will stay constant. But here it's quite different. It will not stay constant. So we have to take the peak value and actually multiply that by the reference sign table that we calculated previously. So this is essentially the reference sign table. Essentially what we're doing is we're just taking the sign of each value over the entire switching cycle. So obviously the array size is 100, and we just say I divided by the array size multiplied by 2 pi. And essentially what that does is it gives us the sign value at each point, at each reference point. So we're essentially going to have 100 unique points, in this case unique references. So essentially what we've just done by implementing this is generate this this table, and the lines obviously represent discrete points. We'll essentially calculate that. So just imagine the lines drawn all across is in total for the 20. Actually, let me just show it. So over here, that will be 10 milliseconds in this case, and that was 20 milliseconds for 50 hertz, for the 50 hertz reference signal. And these lines, so this is actually 50 unique values, and 50 from 10 milliseconds to 20 milliseconds, making 100 total. In this example anyway, that's what we're using. We're having 100 reference values. So we're just going to go back, and that's essentially what we have here. And now we actually have to get the real reference. I apologize for this oversight. So what we get in here is a value between 0 and 1. So we actually have to scale it to get the real reference. That's why we have to multiply by this value, which is the peak value. And obviously we get this by multiplying our desired VRMS multiplied by √2. And we're able to actually get this peak. So essentially the peak value of our sinusoid would be 325.269. So essentially multiply that by the sine values obtained from the reference sine table. Well, the values obtained from taking the sine of each value over the reference period. So going over back to the timer one. So that's the first thing we're going to do. So we're going to take that value. So the VAC ref at this point in time will be that value for this particular element of the array ref sine table. So at this point, obviously at the start, it will be 0, and then 1, and then 2, and then 3, etc., all the way to 100. And obviously here we have to basically check, rectify that value as well. The VAC ref that we've calculated, obviously, as you can see, it goes negative as well. We need to rectify it. So obviously that's what we're doing here. So if VAC ref is less than 0, we need to make it positive and multiply by the negative of itself. And then if VAC is greater than 0, actually this is not necessary. Let me just take that out. Oh, apologies. So just go ahead and do that. Yeah. All right, and now here is essentially where the, I suppose, control is. It's the same as before, plus, plus, minus, minus, what I kind of call it. So we're gonna, if the VAC value is less than the VAC ref, so the VAC is the value that we actually sent at that point in time, and obviously the VAC ref is a constantly moving reference, and if it's less than that reference, we're going to increase our MA value, amplitude modulation index, and if it's greater, if VAC is greater than VAC ref, we're going to reduce our amplitude modulation index by this value. Obviously, same as before, if you increase this value, you're going to get to the set point quicker, even quicker than we already would, considering the new method that you're utilizing. You get there quicker, but obviously it'll be a bit more unstable, so you have to find that sweet spot that works for you. And obviously, as you can see in this case, you could use more advanced controls like PI control. I'm not using it in this case due to obviously restrictions with regards to the microcontroller speed. It will take more time out of the system if I was to do it in floating point anyway. I suppose using integers, everything will be much faster, but that's a topic for a whole different video. So afterwards, once you've calculated the MA value, once you've obtained that MA value, you can basically limit in it. If the MA is greater than 0.95, you're going to equate it to 0.95. If it's less than 0.0, you're going to equate it to 0.0. And obviously, you need to obtain the PWM, the duty cycle, the true duty cycle values. Obviously, first you'll multiply by the sin1 array. The array obtained previously, you multiply it by that. You add it to 0.5, and obviously you scale it to a duty cycle that can be understood by the microcontroller. And obviously after that, you basically update the duty cycle. So that's essentially the method of, I always forget this. And finally, obviously, you have to obviously move to the next point of the array, move to the next element of the array. And obviously if the arrays there's overflow has occurred, we have to start again because it's a sinusoid, so we have to do it again. Start from the bottom again, the lowest value. All right, and this is basically using the sinusoidal reference method. There's a little more steps to it. There's obviously more little bit different from what it was before, but you get much better accurate results doing this. You have a much better controller, especially talking about closed loop control of an inverter. You have much better control. You get to the set point much quicker, and it's just a little bit different from the other method. I wouldn't say it's much more complex. It just takes some getting used to. So I'm just gonna go ahead and explain it again, and obviously use aspects as we discussed before. So I'm just gonna take this and use that down here. So obviously calculating the VAC, we're using the same formula, same ADC resolution 10, raw ADC value that will be found in the ADC 1buff0, the ADC buffer, the offset, sensor gain factor, obviously in this case 230, and the VRF is obviously 5 volts. It won't always be this values depending on the microcontroller you're utilizing and obviously the type of sensor you're using. But this is just the general guide to ensure you arrive at this particular formula. And next, obviously, as we discussed before, I'm just going to be copying the same because it's literally the same comment. So we're rectifying over here, we're rectifying the AC voltage. And next we're actually, so this is not included in the previous one, obtaining the AC ref. So which so it constantly changes. So it's constantly changing. It never stays the same depending on the element that we're dealing with. So essentially we've obtained this reference sign table, which is nothing which is nothing interesting. All we're simply doing is we're taking the sign value over the reference period. That's it. So we're taking the various sign values. So you can imagine we're basically taking 100 different sign values. Actually, it will be much simpler to just simply explain it in the sense of it's a sign function. It's a simple sign function, but we're basically digitizing it in a sense. So we're breaking it up into parts. So instead of it being analog, we're basically taking essentially samples of it over a 20 millisecond cycle, over the reference period, let's say. So that's essentially what we're doing. And we're multiplying that value by our desired peak. So in this case, our desired reference peak is 325.269. Okay, this is really bad, but that's basically 230 V. Wow, this is going to be a mission to write that RMS. So this 230 VRMS is just an example, but essentially that will give us a peak of 325.269, and basically just taking the sign and just multiplying it by that. And just go back to talking about, and that's what we're doing in this step. And this step is very crucial. It's the most important step using this particular method if you want to use this particular method. And obviously after that you want to rectify that value. Rectify the VAC ref value. And obviously you might ask, what's going to happen if we don't rectify? Well, then we're going to need two of this. because when it's negative, it's a different rule. Now you got to do everything in the opposite fashion. And yeah, obviously you can play around with it and see what gives you the best results. Obviously, you go ahead and do that, but I find this to work out just okay. So this VAC ref value, and obviously this is where we simply increase or decrease MA. Decrease MA based on VAC and VAC ref. All right. And obviously, well, the rest is kind of the same. I could literally just copy and paste the rest of it. Obviously, so just limiting, just trying to keep the comments consistent between both of them. It's essentially doing the same thing. We're just updating the PWM1 and PWM2 variables, and update duty cycles for both hop bridges. You might also be wondering, why did not just say OC1RS equals to that? You could go ahead and do that. I prefer to do it this way. It's a little bit redundant, obviously, but it's just a choice that I've made. And keep track of the array element. This is very important. And there we are. And obviously, finally, you want to restart the array if overflow occurs. All right. I'm just going to go ahead, run this code. Well, before I actually do this, it's important that I go back here and actually change this. So like I said, the previous MA, with the previous method, I had to start with an MA value, which was a little bit higher, just so we could get there, get to the set point within a particular time window in the simulation tool. So now I'm just going to change this MA value. I'm just going to make it lower, because with the current method, it will get to the set point much quicker. That's kind of the point of it. Right, so I can just go over to Proteus. Okay, and just run that. Well, it's gonna take a minute, so just gonna go ahead and skip to the end. All right, so it's kind of almost done at this point, so we can just it's almost there. Okay. Simulation log. Alright, there we are. And obviously, we could also see some certain issues generally it arrives at the set point sooner than the previous method. You might be looking, while the previous one arrived there actually sooner than this. Just keep in mind that the MA value is a bit lower. So the best way to demonstrate this is just go back. So as you can see, by the 240 millisecond mark, it's kind of already at the set point, which is about, yeah, because it's actually checking at every point. So it's not waiting for 10 milliseconds or anything like that. It checks at literally every point, because we're comparing an array. We're using a reference sinusoid. So just to show the difference in speed of well, convergence speed, let's say, to get to the set point. So let's say it gets there about 235, 36 milliseconds. So I'm just gonna go back and go back to the firmware. Just close Proteus. Go back to the firmware, leave it at MA, and then go to the timer one actual interrupt code, comment that, and go back to the peak method and actually run that. to actually show what we are talking about. And go back to Proteus. Alright, so this is going to take a while, so I'm just going to skip right over to the end. Alright, so it's going to close. Well, this is just to basically illustrate the difference in the two methods, or the benefits of the second one over the first. Alright. It's done. Okay. There we are. So the first one converged right around here, actually. So the cursor was already there. And where are we? We're around 222 max, not nowhere near 325.269. Even going over to the end, which is at like 440 milliseconds, is still slowly, steadily going up there, getting up there. I don't know how long it's gonna take to get up there. Probably at this rate, I don't know, by guessing by a second, it should be there. And obviously that is an advantage. Obviously, well, it is technically, well, it is closed loop control, but it should be noted that it does have drawbacks with just detecting the peak. It's safe but simpler, but it does have drawbacks. But if we take a look, like we saw previously, if we just go back to the firmware, and if we use the sinusoidal reference method, there's a bit of a change that you have to take note of, and you do need an array for just simply for the reference, but it is worth it in my opinion to actually use this particular method, to use the sinusoidal reference method. And I'm just gonna go back and actually change the set point to 120 VRMS, which is like about 169 magnitude. There's probably some other decimals there. So I'm just gonna run that. So this represents something, and I'm actually Proteus, and I'm just gonna go ahead and do that. Well, it's gonna take some time, so I'm just gonna go ahead and sort of skip to the end. And right, so it's almost done. %. Okay. There we are. Well, it takes almost no time, I guess, because it's closer this time. But that's about it. And obviously, for much better results, I'd encourage more elements in the array. So to eliminate this, I suppose, weird jitter over there. Yeah. And that's about it for closed loop control of an inverter. So we here basically presented two methods. The first, the peak, and the second, the sinusoidal reference, both with the positives and the negatives. And that's about how you implement closed loop control of an inverter. So all the best in your applications with this. Obviously, the code will be linked to it anyway, will be in the description. And cheers, have a good one.